Hi, this is Graham Helfrich, Technical Advisor Manager for the Engineering Software here at IHS Markit. Welcome to the weekly Did You Know episode, where we learn how to do something of value that you probably didn't know about your IHS Markit engineering software. Today's topic is about predicting buildup time in unconventionals. Now, we already know buildups can take a really long time in these low permeability wells, but today I'm going to show you how you can actually predict that buildup profile. We're also going to check out how our buildup profile can differ when our matrix permeability is 10 microdarcies, 2 microdarcies, or 500 nanos. And we're even going to see how that buildup profile can change when we're below the dew point or bubble point. So here we are in Harmony Enterprise. I've got a gas condensate well, and I've created a horizontal multi-stage frac. And we can see with this reservoir description that I'm using the EFR model, and we have long fractures, and the green area is our matrix permeability. So we can see the history match below looks quite reasonable. So how do we predict the buildup profile? Well, we go to the forecast, and normally this is where we would predict our production rate into the future at drawdown. But in this case, we're going to predict a buildup. So I'm going to put a 10-year forecast, and instead of a gas rate or a drawdown, I'm actually going to force the gas rate to be 0. So just type in 0. There. Okay, so what we have is a 10-year forecast at a production rate of 0, meaning what we're seeing is the calculated sand face pressure into the future. And the blue line is the average reservoir pressure. So we can see in this case we've got 1.3 microdarcies in the SRV and 30 nanos in the matrix. And this is our expected buildup pressure. Okay. Now, one of the things is whenever we do these history matches, these are non-unique models, so we'll often rely on the probabilistics or risk analysis. What I've done is I've made a second reservoir model here, and I've tried to make this very different. I have the SRV running totally along the lateral, and my fracture half lengths are a lot shorter. As a result, I have to use a higher permeability in the SRV, and let's see what the results are. Well, I get a history match, right? This is part of the non-uniqueness of transient flow. We can use different combinations of XF and SRV permeability like we have here. But what impact does this have on our buildup profile? Okay, well, here are the results. We can see in the history match, they're both very, very similar. But we can see in this particular case, the buildup profile is a little bit different for this history match where we have long XFs and low SRV permeability. And this is the buildup profile, again, when we have a great history match, but with a different distribution of the SRV. And I should say, in both of these models, the SRV area is 25 acres in both of them. And the total volume of the reservoir is also the same, and we can see that by the average reservoir pressure. So this just gives you an example of how you can do a sensitivity on your expected buildup profile using different potential reservoir descriptions. Okay, the next thing I want to show you is predicting how the buildup profile may look different for very different matrix permeabilities. So this is an oil well, and in this case, I've got my fractures, I've got my reservoir description, and I've entered 10 microdarcies for the matrix, so pretty high. So again, going to my forecast, what I've done here is I need to assign some sort of drawdown, and what I've done is a 12-month forecast, and instead of entering my drawdown, I've asked the model to maintain a rate of 500 barrels of oil per day. So this is an input. As a result, for the first 12 months of production, the brown line is the required drawdown in order to maintain 500 barrels per day. So the brown line, this is the model's prediction of the drawdown required based on this reservoir model. So I've done that for 12 months. Then I've asked for 12 months of shut-in, 0 rate. And that's this point here where we start to see the buildup. So in this case, I actually reach my average reservoir pressure after about 1 year. Okay, so this is one model. What I've done now is I've duplicated this process, but all I've changed is the matrix permeability. Okay, so again, the same reservoir description, but I went from 10 down to 2 microdarcies in the green area. That's all I changed. And then I've also done a final one where I use a very low permeability, in this case 500 nanodarcies in the matrix. So these are the only difference between the models is their matrix permeability. In each of them, I've gone ahead and done the same sort of constraint where I ask it to maintain 500 barrels per day for a year and predict the drawdown, and then do a shut-in for 12 months to predict the buildup pressure. So let's look at these results. I sent them all over to the comparison plot. Okay, we're going to look at these one at a time. So the first thing we see here, this is my 10 microdarcy, my high permeability case. So we get the required drawdown in order to maintain 500 barrels per day. We shut in and we get the predicted buildup, which in this case will reach average reservoir pressure after a year. Next, we're going to reduce the permeability in the matrix down from 10 to 2 microdarcy. Now what's really cool here is in order to maintain that same 500 barrels per day with the lower permeability, a higher drawdown is required in order to maintain that same rate. So that's really neat. And as a result, this is our predicted buildup profile with 2 microdarcies. The overall shape is quite different compared to the higher permeability up here. So what about 500 nanos? Well, we see with the lowest matrix permeability, we need the strongest drawdown. We need to basically pull on the well the hardest in order to maintain 500 barrels per day. Now something interesting is happening right here. The shape totally changes. For this particular well, the bubble point pressure is 2,000 pounds, which is right here. We see that something is really changing here. In fact, the gas rate starts to really take off once we drop below the bubble point. And then even the buildup profile is very different until we get back above the bubble point pressure, and then the profile is different. Let's have a closer look at this last case. Okay, so this is our 50 nanodarcy case, the lowest case. We're going to look in here and we're going to just have an inspection about what's happening with the pressure and saturations around the fractures. So when we go back before any production happens, we have equal pressure everywhere in the reservoir. And once we start producing at that constant rate of 500 barrels per day, we see the drawdown and we see that pressure, of course, that is going to be predicted and the drawdown required to maintain that rate. Once we shut the well in and we start the buildup, which is this brown line right here, we see that the pressure kind of starts to equalize a little bit more. Okay, so this is basically looking at the pressure. When we look at the drawdown profile again, this is when we drop below the bubble point pressure of 2,000 pounds, and that drawdown profile really changes, and the buildup profile as well at the bubble point pressure. So what I want to do is check out the gas saturation through time here. Okay, so if I go back to the very beginning, I've got no gas saturation in the oil reservoir. As I keep producing the 500 barrels per day, I see that my gas saturation is still 0. But watch what happens once the drawdown gets to 2,000 pounds, or the bubble point pressure. Now we start to see that solution gas coming out of the oil, and that really changes the drawdown profile that's required to maintain 500 barrels per day. Okay, so now we're at the point in time where we're going to shut the well in, and we've got about 12% to 8% gas saturation near the fracs. So let's start looking at the buildup. Okay, so the pressure's building up, and I'm approaching the bubble point pressure. The pressure's rising, and I see that the solution gas is actually going back into the oil as the average pressure increases near the fractures. Okay, now we're above the bubble point, and that buildup profile changes again now that we're in single phase flow. So this is really interesting just to see how this impact on both drawdown and the buildup will change whether you're above or below the bubble point. And you can do the same thing for gas condensate with the dew point pressure. So what does this mean for you? Well, the first thing it means is you're able to predict your buildup profile for your well that you have a history match on. And we saw how we can even create a range for that, making different assumptions about our reservoir description. The other thing this means for you is when we have some uncertainty about our matrix permeability, we can actually predict how that buildup profile may look with different drawdown requirements to maintain a rate, and also the expected buildup profile if we shut the well in. And also, finally, if we do drop below the dew point or bubble point, how that can change the profile of our drawdown requirement and the buildup. And that's it. I want to thank you for your attention. If you have any questions, just give me a call or email me, and subscribe to be notified of next week's Did You Know episode.